Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 2 of problem set 17, Kinetic Molecular Theory. Okay, number 6, it says, at a given temperature, a gas A diffuses twice as fast as gas B. What is the relationship between the molar masses of the two gases? Okay, well, we know that when we're looking at diffusion, right, when we're looking at speeds of gases, we're really looking at the RMS speed, okay? And then when we're relating one gas to the other, right, if I want to get a ratio of one to the other, I really just divide one by the other. So I'm gonna put A on the top, let's say, and then URMSB on the bottom. Okay, so now I'm going to get a ratio of their speeds, but within their speeds, you know that there's an equation for each of these that has their molar masses in it that can actually help me relate them to each other, so the molar masses to one another. So doing that, if I know that each one here is equal to each one of these equations, right? All I've done really is replace each of these with this equation, okay? And what we can do is actually combine like variables and cancel out a lot of these variables. So if you remember from algebra, if a square root is on the top and the bottom, it's actually under the same square root. So I'm going to do this, square root the whole thing. Now I got 3RT over molar mass of A all over 3RT over molar mass of B, okay? Now, hopefully you've noticed that these 3RT is going to cancel because we're at the same temperature, right? At any given temperature, they're going to be at the same temperature, and then the R is a constant and the 3 is a constant, so those all get canceled. So then I get the following, the square root of 1 over m of A over 1 over m of B. Now, when we do this, this actually becomes now the overall denominator, and this flips right here to become the overall numerator. So what I get is actually the square root of molar mass of B over molar mass of A. Now, that's in relation to this equation. So really, this equation right here is one that you should know. It's actually super helpful when you're looking at speeds and trying to relate their molar masses. So they told us that the gas A diffuses twice as fast as gas B. So now I know that this value right up here is technically 2, right? And this would be 1, proportionally to each other. It doesn't really matter the value because you're still going to end up with 2. So I'm going to say 2 is equal to the square root of m of B over m of A, and then just get rid of the square root. So I'm going to square both sides. I end up getting 4, which is just the relationship of the molar mass of B over the molar mass of A. Now, what does this mean? This means that the molar mass of B is 4 times higher or 4 times bigger, heavier, than the molar mass of A. Okay, so knowing the speed can actually help us relate their molar masses by this equation simply because we're using the RMS equation to get a ratio between the two, okay? So part B says, an unknown gas diffuses 3.728 times slower than hydrogen gas at any given temperature. What is the molecular weight of the unknown gas? Okay, so now here's what I'm going to do. I'm going to say URMS, and I'm going to put hydrogen on the top here, and I'll explain why here in a second. And then URMS, we'll just say of gas X. Okay, we're just going to say X. So what they told us is that this gas is 3.728 times slower than hydrogen, which means that hydrogen is that many times faster. So what I'm going to do is I'm going to put 3.7 set this equal to 3.728, because in reality this would be the 3.728 value in my ratio, and this would be a 1. Okay, and so we just end up getting that value. Now they want us to relate the molecular, find out what the molecular weight would be if that is how much faster hydrogen moves than the other gas. So remember, this is going to be equal to the square root of m of, in this case, we're going to put m of X on the top and then m of hydrogen on the bottom, okay? So firstly, I have to square both sides, okay? I got to square both sides. So in order to do that, I get square here, okay? I end up getting about, let's see, we'll just leave it as squared, actually. We'll just say squared, okay? And then I'm going to multiply the molar mass of, well, let's get this over here. So I still have m of X over here, and then molar mass of hydrogen. Now, the molar mass of hydrogen is about 2.016. So I'm going to put 2.016 over here. And then I'm going to multiply that over. And then that way I get the molar mass of X to be 2.016. And this is going to be what? Grams per mole, right? Times, and then 3.728 squared. Okay, you end up getting, or should get, about 28.02 grams per mole. Now, you may be wondering, like, how do I figure out what gas that is? Well, you can kind of just look at, like, the basic. If you look at the noble gases first, and you find that there's not one of those gases that has that molecular weight, what I would do is then look at the diatomic molecules that you should know, like Brinkelhoff. Okay, these guys. Each one of these guys is diatomic in nature, okay? And if you can find one of these that has this molecular weight, then that will help you usually. So if you can't find in noble gases, okay, then go to Brinkelhoff here, and Brinkelhoff will just and look at the molecular weights. In this case, it ends up being nitrogen because nitrogen's molecular weight by itself is 14, but there's two of them. It's diatomic, right? So that's what Brinkelhoff means. Each one of these are diatomic in their pure elemental form. So this ends up being N2 gas, okay? So N2 gas. So that's a long, messy way to get from a ratio of rates to a ratio and ultimately a numerical value of molecular weight. All right, number 7, it says compounds sensitive to oxygen are often manipulated in glove boxes that may contain an atmosphere of pure nitrogen or pure argon. Okay, a rubber balloon filled with carbon monoxide was placed in such a glove box. After 24 hours, the volume of the balloon was unchanged. Did the glove box contain N2 or argon? Okay, so the volume of the balloon was unchanged. What does that mean? If I have a balloon and I put it in an environment, remember, any balloon, you'll notice over time that a balloon will deflate over time because the gases that we usually put inside balloons, especially helium balloons, diffuse faster out of the balloon than they enter into the balloon. And so the balloon ends up deflating. And so what we're looking for is looking for a gas that might be similar to the one that's inside the balloon on the outside because it's moving at the same rate or it's diffusing at the same rate that the other gas is and maintains the same volume. Now, the only way that we can really relate those is, first of all, we have to assume that they're at the same temperature, which we're going to have to assume, and that the only thing that differentiates any of these gases is their molecular weight. So if we look at carbon dioxide, right? This is filled with carbon monoxide, CO. Okay, this is 12 grams per mole. This is 16. Okay, so that's about 28 grams per mole. Okay, so I'm going to look for a gas that that might have the same effusion rate as carbon monoxide that has a weight of 28 grams per mole. If I look at the molecular weight of each of these, okay, I get about 40 here and about 28 here. Okay, and so I'm going to assume that nitrogen's on the outside because if it's got the same molecular weight, it's effusing into the balloon at the same rate that carbon monoxide is effusing out of the balloon. And so it maintains the volume, the same volume. Now, obviously, it's not going to be pure carbon monoxide anymore in the balloon, but it's still going to have the same volume because the effusion rates of both the gases on the outside and the inside were the same. All right, number 8. It says describe the difference between force and pressure. And I've typed out some notes here that I think will help. So it says force is the product of the mass of an object and acceleration due to gravity. You've probably heard of F equals ma. Okay, that's where that comes from. Now, force is in terms of what unit? It's in terms of newtons. And it's a type of force, but it's not designated over a particular area. It's simply a force in one direction. It's a vector. Okay, that is all a force is. Okay, you've got a mass. You got some sort of mass with in kilograms, and then an acceleration of meters per second squared. Okay, and this right here, a kilogram meters over second squared, is a Newton. Okay, so all it is, and remember, all it is a vector. Now, a pressure is a force exerted by an object over a given area. So now I'm not only looking at the force. Now, let's say I've got I've got a ball, or let's say I've got a box. Okay, let's say this is 10 kilograms, and let's say this is also 10 kilograms. Okay, we're going to start 10 kilograms. All right, so now if I were to ask you between these two, maybe this is not a great representation, but between these two, 1 and 2, which one would you expect to have a greater pressure on the ground? Okay, on the ground. And hopefully you're kind of seeing here, because this area on the bottom is smaller, okay, it's going to have a greater force. It's like, if you can imagine, you would rather get stepped on by, let's say, a clown shoe, right? You'd rather get stepped on by a clown shoe rather than a high heel, right? High heel is the reason is because it's taking almost the same weight and distributing over a smaller area, and that's what a pressure is, okay? So the force is still coming down, right? Same force is hitting down, but the area at which it is being applied is different for each one. So when it's spread over a larger area, obviously the pressure is going to go down. And so what we have is this inverse relationship between pressure and area. We end up getting an equation that looks like this. Pressure is equal to force over area, okay? So as force increases, obviously your pressure increases, but as area increases, your pressure decreases. Okay, so let's if I had the same, let's say another 10 kilograms on this shoe and another 10 kilograms on this high heel, right? Obviously there's some weight over here as well, but if we focus on the heel here, if let's say somebody was putting just all their weight on just the heel part and it was like tilted up or something. Okay, obviously this area is a lot smaller, and so the same weight applied to a smaller area is going to hurt a lot more because the pressure is higher. Okay, so obviously we went over force, the force equation, and then pressure is equal to force over area. So applying that to part B here, it says, why is it easier to travel over deep snow when wearing snowshoes shown to the right rather than just boots? Obviously I don't have them shown, but they look something to the effect of something like this. You have like the shoe part. If you're not familiar with it, it's pretty common in Utah, I feel like, but it's got this shoe part, but then it's got this like range on the outside that spreads out the weight. So you got kind of like this extra area over which you're spreading the weight. And this just makes it easier to travel in snow because what you're doing is you're applying the same weight, but you're applying the same force, right? The weight, your own weight, but it's being applied over a large area, okay? And so it's easier to travel over deep snow when wearing snowshoes rather than boots, because the boots, if you just wore the boots like this, right, smaller area, and it's going to push down. When you use snowshoes with these large, almost like a little snowboard almost, it's going to spread out that area, and you're going to be able to travel on top of snow, even if it's easy to sink in because it's spreading your weight. Okay, so part C says, why does an ice skater exert more pressure on ice when wearing newly sharpened skates than wearing dull skates? So if you can imagine, we're going to zoom up on, if we have a skate here, it's not going to be a great depiction here, but we got something like this. Okay, and if we zoom in on this, okay, if in situation 1, this is super sharp, right? This is super sharp, and then in situation 2, it's kind of dull, right? Right? If this is the end here, this is the bottom. Okay, obviously this area is a lot smaller, so the pressure is going to be a lot higher here than it will be in this situation 2. All right? All right, last one, number 9, says, convert the following pressures to the indicated units. Okay, so one thing that will help you a lot is knowing the conversion units from your equation sheet, and I've just included them here. Okay, so 1 atmosphere is equal to 760 torr, which is the same as 760 millimeters of mercury, and so on and so forth as far as pascals and bars go. So I've only included 3. They probably had like 6 or 7 for you, but I've only included 3, and I really just want to focus on the dimensional analysis here, because as long as you know these, it's just a matter of setting it up. So they want this in pascals. So what I do is I write the measured value first, right? And then 694 torr. Then I'm going to put that conversion here, this one on the bottom here, because I know it's going to cancel out with something else. Now pascals is this 101.325. So I'm going to put 101. Whoops, not 0.325. Okay. And that ends up getting me about 92,524 pascals. Okay, so that's how you want to set it up. You want to use the value, the measured value that they give you. Okay, put it first in the dimensional analysis. Then using these conversions down here, whichever unit you're dealing with, put that in the denominator on the opposite side, and then the other one in the numerator on the opposite side. So that way your units cancel and you end up with the unit that you're looking for. So in the second example, we got 3.5 atmospheres. Okay, I'm going to put obviously 1 atmosphere here on the bottom. And then I'm turning this into torr, so I'm going to put 760 torr. Okay, and this will end up becoming just kind of second nature to you, I feel like. You do this so often sometimes in Chem 105 that it just becomes like another sense almost. So if you do that correctly, you should give it about 2,660 torr. Okay, all right, and then the last one, 5.0 times 10 to the 6th pascals. And then I would put 101.325 pascals down here, and they want this in atmosphere, so that's going to be 1 atmosphere. And then I'm just going to put another little box down here, and we've got, if you do that correctly, you should get about 49.35 atmospheres. Now, some of you may be asking, what about Sig Figs? Well, I didn't apply Sig Figs here, but maybe you should. So in case you have to, what I would do is look at what we have here. We have 3 Sig Figs here, so I should have 3 Sig Figs here. So it's a little hard to do this, but just look at this number and figure out how to make it 3 significant figures, because if you look at it, we've included 5, which reality we really shouldn't have. So it says 92 point. This should be what we should be saying is something to the effect of 9.2 times 10 to the what? 1, 2, 3, 4, 5. 9.25 times 10 to the 5 if you're looking for Sig Figs. Here we've got 2. In this case, I would probably just put 2,700 torr if you're doing Sig Figs. And then lastly, probably just 49 atmospheres. Okay? All right, so that'll finish it up for part 2 of problem set 17, kinetic molecular theory. I hope that was helpful.